Welcome to the second part of Lesson 3. In this part of the lesson, we are going to turn our attention to the reactivity of alkenes. We will learn about a fundamental type of organic reaction, known as an addition reaction, and we will learn how to describe their mechanisms and predict the products of these reactions when they occur on alkenes. The table below shows a summary of the addition reactions for alkenes that we will learn in Lesson 3. Notice that in each case, the starting material, which contains a C-C double bond, is converted into a product where new atoms are attached at the carbon atoms of the alkene. Two new sigma bonds are formed, but the pi bond between the two alkene carbon atoms is broken. This is the defining feature for addition reactions to alkenes. We are converting an unsaturated functional group to one that is saturated by adding one atom to each carbon of the double bond. For each of these reactions, we will study the effects of varying the structure of the starting material, the reagents that cause the reaction to occur, and we will learn to predict the structures of the products that form based on these changes. As we learn these reactions, you are encouraged to construct your own summaries of the reactions that are discussed, including examples that are presented in the lesson video and homework problems. You should be able to visualize and recall this information without reference to your notes in order to understand and explain these reactions on exams and in your future courses. Let's go to the next page and start learning about the first addition reaction of alkenes, hydrohalogenation. The treatment of alkenes with HX, where X equals chlorine, bromine, or iodine, results in an addition reaction called hydrohalogenation, in which the atoms H and X are added across the pi bond. We can see an example of this reaction in the scheme below, which shows the symmetrical alkene cis-3-hexene undergoing the addition of hydrogen bromide, HBr, at the reduced temperature of -30 degrees Celsius. The product, 3-bromohexane, is formed in a 76% yield. So in this reaction, we are seeing the addition of the two atoms of the hydrogen halide, H and Br, to each of the carbon atoms of the double bond. We can generalize this process by using the symbols X and Y instead of H and Br, and noting the following changes. First, we see that the pi bond within the alkene breaks, and the sigma bond between the reagent XY also breaks. Two new bonds are formed, however. The two new bonds are formed between one of the carbon atoms of the alkene and one of the atoms of the reagent, X or Y. Also notice that the starting material was unsaturated, but that upon addition of X and Y, the two carbon atoms that were pi bonded previously are now completely saturated. No additional atoms can be added to these two carbon atoms, as they have the maximum number of sigma bonds present. Look closely for a moment at this reaction. On the next page, you will be presented with several similar, but different, examples of this reaction, but the product will be missing from the reaction equation. When we look at those examples, test yourself to see if you can accurately predict the structures for the products of those reactions by recalling and extrapolating the details from this example transformation. Using the examples below, test your recall for the hydrohalogenation reaction presented on the previous page. Do this by pausing the video and drawing the structures for the expected products for each reaction. When you unpause the video, each solution will be presented, one at a time, from top to bottom. Pause the video in between each solution, and verify your answer before unpausing and looking at the next solution. This way, if you made an error, you can try to correct the error on the next examples before seeing those solutions. Ready to start? Go ahead and pause now. For the first solution, we are adding an H on one atom of the double bond and a Br on the other, and we are removing the pi bond between the two carbon atoms in exchange. Notice that I have drawn two structures. Which one of these is correct? That's right, both are correct, because the two structures are actually identical with each other. Notice that if we name either structure, using the rules of nomenclature we have learned, we generate the same name. This means that the two structures are, in fact, identical. Also notice that the starting alkene happens to be symmetrical. If we draw a line down the middle of the pi bond, we can see that the left of the molecule and the right are the same. Another way of saying this is that we could generate the same name for the starting material, regardless of which end I started numbering the parent chain. So, did you draw either of those two structures for the predicted product? That's great! You only needed to draw one of those structures, or any structure that has the same name, to have answered that question correctly. Are you ready to try the next example? Go ahead and pause now. In the solution to the second example, we will start by drawing the cyclohexane ring. We keep the ring intact because we are not breaking any of the sigma bonds that would split the ring apart. We are, however, breaking the pi bond, and adding a hydrogen atom and a bromine atom to each carbon that were previously in the double bond. Would it matter if I had drawn the structure with the bromine on this carbon, rather than the one adjacent to it? No, for the same reasons we discussed in example 1. Any version of the structure of one bromocyclohexane is correct for this answer, as long as you have a single cyclohexane ring with a single bromine substituent, and nothing else attached. Notice that I am not drawing the hydrogen atom that was attached during the reaction. It is not necessary to draw the hydrogen atoms we add in these reactions because, as you know, skeletal structures allow us to omit them, as they are implied in the structural drawing. Are you ready to try the next example? If so, go ahead and pause the video now. Do you notice anything different structurally with the third example? That's correct. The structure of this alkene is not symmetric. Notice the number of hydrogen atoms attached at each carbon atom is different on either side of the double bond. We have 2 hydrogen atoms at carbon 1, and we only have 1 hydrogen atom attached at carbon 2. Another way of saying this is that it would matter which side the parent chain numbering started at, because we would generate 2 different names if we started on one side or the other. What does this mean in terms of the predicted product formed in the reaction? It means that there are 2 possible products that can be formed. One of the products is formed when the hydrogen atom is attached to carbon atom 1, and the bromine atom is attached to carbon atom 2. The other product that can form results from the opposite attachment order. If we attach the bromine to carbon atom 1, instead of carbon atom 2, and the hydrogen atom to carbon atom 2, instead of carbon atom 1, we get a different isomer as our product. These 2 products are both possible outcomes of the reaction. Let's go to the next page and look at this in a little more detail. The issue that we just encountered on the third example results in the formation of 2 isomeric compounds that differ by the position of attachment of the 2 atoms being added. These types of isomers are called regioisomers. Regioisomers are a type of isomer where molecules have the same molecular formula, but differ in the connectivity of atoms within the molecule. This concept is particularly important in organic chemistry, when dealing with reactions involving unsymmetrical molecules, like the example shown here. Addition of HX, an unsymmetrical reagent, to an alkene that is also not symmetrical, i.e., there are different substituents on the C-C double bond, leads to the possibility of producing 2 isomeric products. These products are regioisomers of each other. In practice, it is usually observed that only one of these regioisomers is produced in a significant amount. This is called the major product, and the alternative is the minor product. This observed preference for the formation of one regioisomer over another is referred to as regioselectivity. Regioselectivity refers to the preference of a chemical reaction to yield one structural isomer over other possible isomers when there are multiple potential sites for the reaction to occur. In other words, regioselectivity describes the tendency of a reaction to produce a specific regioisomer as the major product, when multiple isomers could theoretically form. How can we know which regioisomer will be preferred, i.e., the major product, and which will be the minor product? Let's go to the next page and look at several examples, where we will learn how to predict the outcome of these reactions. To try to understand and predict the regioselectivity for hydrohalogenation reactions, let's look at 3 examples. For each of these reactions, I will draw both the major and minor products. We will then compare the 3 examples, and see if we notice a pattern that we can use to predict the outcome of the 2 example problems that follow. Here are the major and minor products for the first reaction. Pause the video and draw their structures in your notes. Here are the major and minor products for the second reaction. Pause the video and draw their structures in your notes as well. Finally, here are the major and minor products for the third reaction. Take a moment to pause the video again, to copy down these structures in your notes. Now that we have the products drawn for each reaction, pause the video, and see if you can identify any particular pattern that can help you predict where the hydrogen and bromine atoms are attached when reacting with an unsymmetrical alkene. Now that you have had a few moments to examine the example reactions, pause the video again and see if you can draw the major and minor products for the 2 reaction problems shown here. When you unpause the video, I will draw the solutions and we can discuss the results. Are you ready to try these examples? If so, go ahead and pause the video now. Welcome back. Let's look at the first reaction. The major product for this reaction has the bromine atom attached here, whereas in the minor product, the bromine is attached here instead. Notice I haven't drawn the hydrogen on either product. It is okay if you did draw the hydrogen atoms, as they would appear here and here in the structures, but it is also fine to leave them implied on the skeletal structure. How did we know to place the bromine on this carbon atom in the major product, and on this carbon in the minor product? If we look at the example reactions, we can see a pattern emerge, whereby the bromine atom is always attached to the carbon atom that is more substituted, and the hydrogen atom is always attached to the neighboring carbon, which is less substituted. We can see this in our example as well. We can compare the 2 possible carbon atoms where the bromine can be attached, and label them with their degree of substitution. If you compare the 2 carbon atoms, one has a higher degree of substitution than the other, and this is the carbon where the bromine should be attached. The hydrogen atom should be attached to the other, less substituted carbon. Let's look at the next example. We start by labeling the substitution of the 2 carbon atoms of the double bond. Now, when we draw the structure of the major product, we draw the carbon skeleton of the structure with a new bond to the bromine atom. We make that bond at the carbon atom that is more substituted. The minor product has the opposite attachment, with bromine going to the less substituted carbon atom. What is the cause of this selectivity? Let's go to the next page and take a closer look. To understand what is causing the regioselectivity that we are observing in these reactions, we need to look at the detailed, step-by-step process that explains how the reaction occurs. This step-by-step description of the reaction process is known as the mechanism for the reaction. We will learn the mechanisms for many of the reactions we study, and we will see that most mechanisms are made of only a few fundamental types of transformations, linked together in a sequence that is unique for a specific reaction. How will we describe these mechanisms? Reaction mechanisms that we will examine will all involve the formation and breaking of covalent bonds. Organic reaction mechanisms use arrows to show the flow of electrons between species. In many of the reactions we will look at, the arrows we use to depict electron flow will be drawn between species we will describe as nucleophiles and electrophiles. Before we look at the reaction mechanism for hydrohalogenation, let's first look at the building blocks of organic reaction mechanisms and the arrows we use to depict them, starting on the next page. In organic chemistry, Curved arrows are used to represent the movement of electrons during chemical reactions. They are a key tool in illustrating reaction mechanisms. If we looked at a large collection of organic reaction mechanisms, and we tried to distill the fundamental types of events that occur in all of them, we would find that there are 4 key patterns. Each of these patterns has a name, and an example that we will look at on subsequent pages in the notes that follow. These are the 4 types of events that we observe in organic reaction mechanisms. 1. Nucleophilic attack. 2. Loss of a leaving group. 3. Proton transfers, acid/base reactions, and 4. Rearrangements. For this class, we will limit ourselves to reactions that contain the first 3 of these patterns. I will introduce the idea of rearrangements, but reserve reactions that contain this pattern for a future course. Let's look at each of these patterns, and see how curved arrow notation is used to depict the bond changes that are occurring in each. Let's look at the first of the 4 mechanistic patterns first, the nucleophilic attack. Imagine a scenario where a molecule, called a nucleophile, which is rich in electrons and often carries a negative charge, encounters another molecule, known as the electrophile, which has an electron-deficient site, and usually a positive, or a partial positive charge. The nucleophile, attracted by this electron-deficient site, uses its lone pair of electrons to form a new chemical bond with the electrophile. This interaction is like a magnet, where opposite charges attract. During this process, the nucleophile donates its electrons to the electrophile, filling the gap in its electron structure. This action can cause other bonds within the electrophile to break or rearrange, leading to the formation of new products. For example, consider a bromide ion, an example of a strong nucleophile. Bromide is a strong nucleophile because its relatively high negative charge density increases its reactivity in nucleophilic substitution reactions. Additionally, it has a large polarizable electron cloud that allows it to effectively donate electrons and form bonds with electrophiles. When it encounters a tert-butyl cation, an electrophile with a positively charged carbon atom, the bromide ion donates its electron pair to the carbon, forming a new CBr bond. This reaction results in the formation of tert-butyl bromide. In another scenario, let's look at a nucleophilic attack involving a pi bond. Alkenes, which have a carbon-carbon double bond, can act as nucleophiles. Alkenes are nucleophilic because their pi electrons are loosely held and can easily interact with electrophiles as a result. Additionally, the electron density in the double bond region makes alkenes reactive and capable of forming new bonds in nucleophilic addition reactions. When an alkene reacts with a generic electrophile, represented below as the symbol E, with a positive charge, the pi electrons of the double bond are donated to the electrophile, forming a new bond. For instance, if an alkene, such as the example shown here, reacts with a generic electrophile, shown here as an E with a positive charge, one of the carbon atoms forms a new bond with E, resulting in a carbocation intermediate, which can further react to produce a stable product. In general, we will see 2 types of nucleophiles engaging in the nucleophilic attack process. First, there are lone pair nucleophiles. These nucleophiles use non-bonding electron pairs to form the covalent bond with the electrophile. Imagine a lone pair of electrons, which is not involved in any bond within the nucleophile, being donated to the electron-deficient site of the electrophile, creating a new bond. Second, we have pi bond nucleophiles. These nucleophiles use electrons in pi bonds to form the covalent bond. In this case, the electrons from a double or triple bond are used to attack the electrophile, leading to the formation of new bonds and the rearrangement of existing ones. Understanding these 2 types of nucleophiles, lone pair nucleophiles and pi bond nucleophiles, helps us predict and explain the behavior of molecules in various organic reactions. We will see this pattern of reactivity, called nucleophilic attack, in most of the reaction mechanisms that we encounter in the course. Let's go to the next page and look at another fundamental pattern of reactivity observed in organic reaction mechanisms, a pattern called loss of a leaving group. The second fundamental pattern in organic reaction mechanisms is the loss of a leaving group. This process involves a substrate molecule shedding a part of itself, known as the leaving group, which departs with a pair of electrons. To illustrate this, let's consider tert butyl bromide. In this compound, the bromide ion acts as the leaving group. When tert butyl bromide undergoes a reaction, the bond between the carbon and the bromide ion breaks. This process is known as heterolytic bond cleavage, where both electrons from the bond move to one of the atoms, in this case, the bromide ion. Using curved arrows to represent this transformation, we start the arrow, the tail, at the bond between the carbon and the bromide ion, indicating that the electrons are coming from this bond. The arrow head points to the bromide ion, showing that the electrons are moving towards it. This departure results in the formation of a bromide ion, with a formal charge of -1, and a tert butyl cation, with a formal charge of +1. By understanding this change in the formal charge, we see that the bromide ion becomes negatively charged as it gains the electron pair, while the tert butyl carbon becomes positively charged as it loses the pair of electrons. This clear depiction of the electron movement and the resulting charge distribution is crucial for grasping the underlying mechanisms at play. To summarize, the loss of leaving group pattern is a key step in many organic reactions, allowing molecules to transform and form new products after the leaving group has departed. Through the use of curved arrows, with the head and tail indicating the start and end of electron movement, respectively, we can clearly represent this electron shift and better understand the resulting formal charges and overall reaction dynamics. Another fundamental reaction mechanism pattern is proton transfer. This process involves the transfer of a proton, represented as H+, from one molecule to another. It's a crucial mechanism that often facilitates other reactions by altering the charge and reactivity of molecules. To illustrate this, let's consider the protonation of an acetone molecule by a hydronium ion, represented as H3O+. When acetone reacts with hydronium, a proton is transferred from the hydronium ion to the oxygen atom of the carbonyl group in acetone. This transfer increases the electron density around the oxygen, changing its formal charge and reactivity. In terms of formal charge changes, the hydronium ion, which initially has a formal charge of +1, loses a proton and becomes water, which has a formal charge of 0. The acetone molecule, which initially has no formal charge, gains a proton, resulting in a positively charged protonated acetone. This is also called an oxonium ion. You can see examples of other oxonium ions on your abbreviated pKa table, as they are all strong acids with pKa values below 0. Returning to the mechanism, to represent this transformation using curved arrows, we focus on the electron flow. The tail of the curved arrow starts at one of the lone pairs on the oxygen atom of acetone, indicating that the lone pair electrons are used to form a bond with the incoming proton. The head of the arrow points to the proton from the hydronium ion, showing where the electrons are moving to form the new OH bond in the protonated acetone. Another curved arrow starts at the bond between the proton and the oxygen in the hydronium ion, with the tail at the bond and the head pointing to the oxygen. This arrow indicates that the bonding electrons are moving to the oxygen atom, converting hydronium into water. The proton transfer mechanism is essential because it helps us understand how molecules gain or lose protons, altering their formal charges, and making them more reactive for subsequent steps in a reaction pathway. Let's go to the next page and look at the fourth and final reaction mechanism pattern that we commonly see in organic chemistry. A fourth pattern that is frequently observed in reaction mechanisms is called a rearrangement. In organic chemistry, Rearrangement reactions involve the reorganization of the structure of a molecule. During these reactions, atoms or groups within the molecule shift from one position to another, leading to a different structural arrangement. This process often occurs to form a more stable molecule or intermediate. This is particularly relevant in the context of carbocation stability. Note that carbocations are more stable when they are covalently bonded to more alkyl groups. Let's look at two examples: a hydride shift and a methyl shift. In a hydride shift, a hydrogen atom, with its bonding electrons, moves from one carbon to an adjacent positively charged carbocation. For instance, consider a carbocation intermediate where a hydrogen atom shifts from a neutral carbon atom that is next to a positively charged carbocation. The tail of the curved arrow starts at the bond between the hydrogen and its original carbon, and the head points to the positively charged carbocation. This shift results in the stabilization of the carbocation, changing the formal charge distribution. The original neutral carbon becomes positively charged, while the carbocation that gained the hydride becomes neutral. Similarly, in a methyl shift, a methyl group migrates. The methyl group migrates from a neutral carbon to an adjacent, positively charged carbocation. Again, the curved arrow starts at the bond between the methyl group and its original carbon, and the arrowhead points to the positively charged carbocation. This rearrangement also stabilizes the carbocation, with the original neutral carbon becoming positively charged, and the carbocation that received the methyl group becoming neutral. These rearrangements, involving hydride and methyl shifts, are crucial for forming more stable carbocations, and often lead to significant changes in the reaction pathway. While we won't be seeing these specific reactions in this course, they are a feature of more advanced topics you'll explore in the next course in the series. Understanding the electron flow, represented by the head and tail of the curved arrows, helps us visualize these dynamic changes in formal charges and molecular structure. Now that we have seen the four patterns of mechanisms, let's look at the mechanism for addition of HX to an alkene, the reaction that is called hydrohalogenation. The reaction we will use as an example is shown below. Here are the steps in the mechanism. As I describe the mechanism, I will be annotating in real time, so that you can see how the electron flow arrows are drawn. You are encouraged to pause the video and annotate your own notes as we proceed. Another strategy that also might help involves watching the entire mechanism sequence without writing anything down, and then pausing the video and trying to recreate the steps from memory, going back to the video when necessary to check or to fill in any gaps in the process. You should practice trying to recreate this mechanism in your own notes, to verify that you can recall all of the steps and intermediates in the process. Once you have it committed to memory, make sure you repeat this recall at least once per day to ensure that you do not forget what you have learned. Alright, let's get started with the mechanism. The reaction begins with the double bond in 2-butene acting as a nucleophile. The pi electrons in the double bond are attracted to the hydrogen atom in hydrogen bromide. This happens because of the bond polarization in HBr, where the electronegative bromine atom leaves the hydrogen atom with a partially positive charge. We represent this with a curved arrow, starting from the double bond, the tail, and pointing to the hydrogen atom, the head, in HBr. This results in the protonation of the double bond, forming a carbocation intermediate. This step can be described as a nucleophilic attack by the pi bond, which is acting as the nucleophile. The electrophile is the hydrogen atom in hydrogen bromide. It could also be described as a proton transfer reaction, because we are transferring a proton from HBr to the alkene. To summarize, during this step, we see the following changes taking place. First, the double bond breaks, and the electrons move to form a new bond with the hydrogen atom. As a result, the hydrogen atom, from hydrogen bromide, becomes attached to one of the carbons in the former double bond. This causes the other carbon to become positively charged, because it lost the electrons that were in the pi bond. So the first step in the mechanism results in the formation of a carbo-cation intermediate. This is a key idea, because as we will see in the examples that follow, it is the cause of the regioselectivity that we observed earlier. For now, let's focus on the last step in the mechanism, which explains how the product forms from this carbo-cation intermediate. In the final step of the mechanism, the bromide ion, which is a nucleophile, attacks the carbo-cation. This is an example of the nucleophilic attack pattern. As before, we represent this with a curved arrow starting from the lone pair of electrons on the bromide ion, the tail, and pointing to the positively charged carbon, the head, in the carbo-cation. The final product of this reaction is 2-bromobutane. The addition of HBr across the double bond is complete, with the hydrogen and bromine atoms now bonded to the carbons that were originally part of the double bond. If we summarize the mechanism, we see that in step 1, a proton transfer takes place, generating a carbo-cation intermediate. In step 2, we see a nucleophilic attack, which quenches the carbo-cation, resulting in the formation of our neutral, and thus more stable, alkyl halide product. Let's go to the next page and look at a different example, so that we can try to figure out why, and how, this reaction favors the formation of one regioisomer over another, when an unsymmetrical alkene is used. Let's look at the mechanism for an example hydrohalogenation reaction that we saw earlier. Specifically, the reaction between 2-methylpropene, which is also called isobutene, and hydrogen bromide. The same mechanistic steps that we observed in the previous reaction also occur in this situation as well. The first step is protonation of the alkene. This involves the pi bond breaking, forming a new bond, specifically a sigma bond, between one of the carbon atoms and the proton from hydrogen bromide. Notice that when we make this new sigma bond to the proton, depending on which carbon I attach it, one of two different carbo-cation intermediates is formed. If I attach the hydrogen to the primary carbon, that is, the carbon that is only attached to one other carbon atom, the positive charge is formed on the adjacent carbon, which is tertiary. It is tertiary because it is attached to 3 other carbon atoms. If, on the other hand, the proton is attached to the tertiary carbon instead, the positive charge develops on the primary carbon. These two carbo-cations are not identical. We can clearly distinguish between them. This phenomenon occurs when the alkene we protonated is not symmetrical, meaning it does not have the same groups attached on either side of the double bond. Do you recall what the next step in the mechanism involves? That's right. The next step involves nucleophilic attack. Specifically, bromide, acting as the nucleophile, attacks the carbocation intermediate at the carbon atom that has the positive formal charge. Because there are 2 possible carbo-cations, that means both are theoretically present in the reaction mixture at any given time. If the tertiary carbo-cation is attacked by a bromide ion, the product generated is 2-bromo-2-methylpropane. On the other hand, if the primary carbo-cation is attacked by a bromide ion, the product generated is 1-bromo-2-methylpropane. The mechanism predicts the possibility that both products can be generated. But why is it that the reaction favors the first product, 2-bromo-2-methylpropane, over the alternative 1-bromo-2-methylpropane? A good answer to this question is simply that the favored product is formed faster. This is true. But we might go a little deeper and ask why. Why is the product, which has the bromine attached to the more substituted carbon atom, formed faster than the alternative? To answer that question, we need to compare the 2 carbo-cation intermediates in the reaction. Let's go to the next page where we can discuss this in more detail. When an electrophile adds to an alkene, it creates a carbo-cation intermediate. The position where this carbo-cation forms is not random. It's influenced by the stability of the potential carbo-cation. Specifically, in an electrophilic addition reaction, the more stable carbo-cation will form preferentially, and it turns out that one of the biggest influence on the stability of a carbo-cation is the degree of substitution. A tertiary carbo-cation, for example, with 3 alkyl groups attached, is more stable than a secondary carbo-cation, which has 2 alkyl groups. The secondary carbo-cation, in turn, is far more stable than a primary carbo-cation, which has only 1 alkyl group. A methyl carbo-cation, which only has hydrogen atoms attached, and no alkyl groups, is very unstable. This trend is the primary factor that dictates the regiochemical outcome of electrophilic addition reactions like hydrohalogenation. But we still have a few questions to address about this effect. Specifically, why are more substituted carbo-cations more stable, and why does this stability cause the reaction to produce the major product faster than the minor product? For the first question, we can look at the diagram below to see why alkyl substituents help to stabilize the positive charge on a carbon atom. The stability comes from the electron-donating effects of the alkyl groups through an effect known as hyperconjugation. To understand hyperconjugation, first recall that a carbocation is a trivalent carbon atom. That is to say, it is bonded to 3 other atoms, using sp2 hybrid orbitals. But it also has an empty orbital, specifically a non-hybridized p orbital, that has 2 lobes that are sticking up vertically above and below the plane of the bonded atoms. This empty orbital is the place where electrons would need to go in order to quench the positive charge on the carbon atom. That is where hyperconjugation comes in. Hyperconjugation is a non-bonding effect where electrons, present in a nearby sigma bond, are able to spread into the empty p orbital when the sigma bond is lined up with the empty p orbital. This effectively decreases the positive charge character on the carbon atom because the nearby electron cloud can blanket the empty orbital with extra electron density. Notice that the effect only works when a sigma bond on a neighboring atom is available. It does not work with an atom like hydrogen, because the small 1s orbital does not effectively overlap with the empty p orbital enough to donate electron density. To answer the second question, which asks why does a more stable carbo-cation lead to a preference for one product or the other, we need to look at a few diagrams on the next page. In electrophilic addition reactions, the formation of a more stable carbo-cation is favored and occurs faster than the formation of a less stable one. This phenomenon is primarily due to the principles of reaction kinetics and the energy profiles of the reaction intermediates. Let me explain this in more detail. When a reaction proceeds, it passes through various intermediates, each associated with an energy level. The more stable an intermediate, the lower its energy. In a multi-step mechanism, the rate-determining step, or RDS, is the slowest step. This step has the highest activation energy, compared to the other steps, and therefore, it determines the overall reaction rate. In the electrophilic addition reactions of alkenes, such as hydrohalogenation, the rate-determining step is the step that generates the unstable carbo-cation intermediate. With this in mind, we can see why the formation of a more stable carbo-cation would give a faster reaction rate than an alternative pathway that would result in the formation of a less stable carbo-cation. As an example, consider the addition of hydrogen bromide to propene. When the proton adds to the double bond, it can form either a primary or a secondary carbo-cation. The secondary carbo-cation, with 2 alkyl groups stabilizing the positive charge, is more stable than the primary carbo-cation. The transition state leading to the secondary carbo-cation is lower in energy, making it faster to form. The transition state leading to the primary carbocation, on the other hand, is much higher in energy, making it much slower to form. As a result, the reaction pathway that leads to the more stable secondary carbocation is therefore faster, explaining why more stable carbocations form more rapidly in electrophilic addition reactions. This preference for stability drives the regioselectivity of the reaction, leading to the formation of the most stable intermediate, and consequently, the more substituted alkyl halide product. This regioselectivity has a name. It is called Markovnikov's rule, and the rationale for why it works is the mechanistic explanation that was presented above. So that we can refer to Markovnikov's rule in the future, let's go to the next page and see exactly what it means. Let's define Markovnikov's rule, an important guideline in organic chemistry for predicting the regiochemical outcome of many types of addition reactions. Markovnikov's rule states that when an unsymmetrical reagent adds to an unsymmetrical alkene, the part of the reagent that adds as a positive part, like a hydrogen from hydrogen bromide, will attach to the carbon of the double bond that already has more hydrogen atoms. Conversely, the component that adds as a negative part, like the bromine from hydrogen bromide, will attach to the carbon with fewer hydrogen atoms. As a side note, the other regioisomer that can form, which has the opposite selectivity predicted by Markovnikov's rule, is often called the anti-Markovnikov product. Understanding Markovnikov's rule is crucial for predicting the outcomes of addition reactions involving unsymmetrical reagents and unsymmetrical alkenes. This concludes the second part of Lesson 3. In the next part of this lesson, we will learn to apply Markovnikov's rule to a multitude of other addition reactions of alkenes, and we will apply the concepts from this lesson regarding mechanisms and carbocation stability. See you in the next video.